In this video, we're computing the integral from negative pi over 2 to pi over 2 of the quantity 1 minus cosine squared x, all multiplied by sine of x. And we're going to do this integral in two different ways. The first way we're going to look at it is by just analyzing the symmetry of these functions, and we actually find out there's really no work to do at all in this integral. This is definitely the best approach to take, but you do have to know some things about even and odd symmetry. We're going to follow that up by looking at what I'm calling the brute force approach to the problem. So we just distribute and integrate term by term and evaluate across the limits of integration. And if all goes well, we'll get the same answer. So the symmetry approach to the problem, what clues us into this being potentially a productive strategy is that our interval is symmetric about the origin. And we know some things about the behavior of even and odd functions when we integrate on an interval symmetric about the origin. For example, the integral of an odd function on an interval like this must be 0. And then even functions are symmetric about the y-axis. So the left half of the integral gives you the same result as the right half. Well, in this particular case, I notice that I have an even function in these parentheses, 1 minus cosine squared x. And remember, the way you can tell this is even is that if I replace x with negative x, I just get back the exact same function. And this implies a symmetry about the y-axis. Okay, and then we have the sine function, sine x dx. Well, the sine function is an odd function. If I replace x with negative x, I get the negative of sine x. And we also happen to know that an even function multiplied by an odd function always gives you an odd function. So this entire integrand is actually an odd function, and we're integrating on an interval symmetric about the origin. So we know this thing is going to vanish. Our answer is 0. Now, if you have no idea what I'm talking about with all this even and odd function stuff, that's okay. It's probably normal because this stuff really isn't emphasized enough in the introductory calculus curriculum. And I'll post a link at the top to my basic introduction to function parity. In other words, evenness and oddness of functions. So let's follow this up with what I called the brute force method. We're going to distribute that sine x, and this gives us the integral of sine x minus sine x times cosine squared x dx. And the antiderivative of the sine function is just the negative cosine. And oops, I forgot an x there. And then this second piece has a sine x sitting right next to a power of the cosine function. Well, in fact, the negative of sine x is the derivative of cosine. So we look at this as a function composition, cosine x all squared, sitting right next to the derivative of the cosine function. So we can just see the chain roll backwards here. And we end up with a plus 1/3 cosine cubed x. So we're just working through the chain roll backwards. We notice we have the derivative of the interior function there, so it was relatively easy to see. Now, when you're doing an informal chain roll backwards kind of approach, you should probably check by taking the derivative. So I imagine differentiating this guy. And when I differentiate cosine cubed, I get 3 cosine squared, and the 3's would cancel there, and I have a cosine squared. And then the chain rule says you have to multiply by the derivative of the interior function, which was cosine. So that gives us the negative sine function, and we're back where we started. So we know this antiderivative is correct. Now let's evaluate across the limits of integration, negative pi over 2 to pi over 2. Well, the cosine of pi over 2 is 0. So when I sub in pi over 2 to these two terms, both of them give me zeros, and I have just a 0 contribution from that upper limit. And the same thing happens when I sub in the lower limit. The cosine of negative pi over 2 is 0. So those are gone as well, and we get a grand total of 0 for the integral. And that agrees with the symmetry approach to the problem, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.